Hello, everyone. I hope you can hear me clearly and see me. Welcome to the afternoon session of Toronto Machine Learning Society Healthcare Summit. My name is Aarti Malhotra, PhD student in AI at University of Waterloo. I'm glad to be the moderator for today's session. I hope all of you are doing fine. I'm honored to introduce Dr. Chris McIntosh today. He's a computer scientist trained in computer vision and AI in medicine. He received awards from NSERC, CIHR, and Michael Smith Foundation for health research. His PhD dissertation developed AI-driven methods for quantitative medical image analysis through manifold learning. His past work in AI in radiation therapy has been approved for clinical use by the regulatory bodies, commercialized and deployed in hospitals around the world. May I now request Dr. Chris to present his work on therapeutic curative intent radiation therapy, treatment for prostate cancer, and enlighten us. If anyone has any question, please feel free to post in the chat. We will have a Q&A session after the talk. Over to you, Dr. Chris.
Thank you very much for the introduction and for everyone for having me today. So today I'll talk about a machine learning system for RT from labs to lives. Okay, so first, financial disclosure. This work has been patented, and we also receive royalties from Research Laboratory, the licensee and distributor of our automated planning technology. And acknowledging that this work would definitely not be possible without a very large team and funding from NSERC, the UHN Princess Margaret Cancer Foundation, CIHR, as well as really a lot of doctors and technical clinicians and tech transfer people across the hospital. And of course, all the awesome students in my lab. So first, a little bit of a primer for radiation therapy for those of you who aren't familiar. So here we have basically a cross-section in a CT of a woman's chest, and you can see that some lungs have been delineated, the heart is in the middle here, there's the breast, and in red, there's a tumor. And the idea is that a radiation beam will come across the body and try to treat the tumor while avoiding radiating the heart, for example. So you wouldn't want to come in this direction because then you would obviously hit the heart, but that's pretty safe. And so that machine is called the linear accelerator. Sits in a hospital, looks like this, and the patient will lie down in this bed, and as they lie down in the bed, the beam will follow along a straight line and irradiate the tumor. So that's reasonably straightforward for that particular procedure. But let's take a look at, for example, prostate cancer. So here we have the prostate delineated in green, we have the bladder and the rectum, and the spinal cord, which all need to be avoided, and the femurs as well. And what we see is a kind of a mock-up of what a treatment plan starts to look like at its initial bit of optimization. And so here we can see blue represents areas of low radiation, moving up to red representing areas of high radiation. And initially the treatment can look pretty rough. So of concern, there's a lot of low dose here or medium dose here around the spinal cord, which if it's too much could actually lead to paralyzation of the patient, which is of course very bad. So the doctors look at these statistics, try to optimize the plan, and the plan itself now gets delivered by that same beam, but it actually rotates around the patient. And as it rotates around the patient, a whole bunch of little leaves move in and out of space and block and shape the beam, creating a more complex distribution than that beam we saw in the previous case. So the doctors look at these statistics, and using those, they will add additional objectives and interact manually with this system to be able to better shape the radiation to look something like this. And it goes through this kind of iterative procedure that can take anywhere from hours to days for a single patient to create their personalized care. So there's been lots of studies, and I'll highlight a particular one here, that actually shows some of the issues with this. And the main issue is that because of this iterative high workload, it requires a lot of experience. So here we see an example in head and neck cancer where we have a baseline population. And so these are patients who are seen by a doctor that sees an average number of patients per year. And on the left, we see the result of a patient seen by a doctor that's seen 15 fewer patients per year on average. And they have a 76% increased risk chance of death, versus a patient who sees a doctor that has seen 15 more patients per year has a 50% decreased risk of death. So overall, from the fewest to the most, there's a 3.5 increased times likelihood of death. And this has nothing to do with the patients. This is simply the patients walked into a doctor's office who had seen more or less other patients with similar conditions that particular year. So obviously this is not a desirable state of our medical system. So how does that kind of work for AI? Well, imagine if we had a national database of radiation therapy treatments from all the best hospitals. And what if we could automatically find all the most similar patients and see what their treatment was? So for example, we have a novel patient here, we index into that database, we figure out from that database that these are the three most relevant patients or three most similar, then we could treat this novel patient in the same way that those three most similar patients were treated at those top hospitals. And therefore we could increase the overall level of care. So we thought this was a fantastic application for AI, and we've been working on that for quite a few years now, and I'll kind of go through some of the results and studies today. So the first step of the process is to encode the patient in a way that the AI can actually understand. So for this example, we have here an input CT image. It has a clinical contour for the prostate drawn on it. And we can start off with some simple filters. So these are Gabor filter responses. And it turns out these are actually very similar to the filters that are learned by the first few stages of a neural network. So they're basically edge detectors. So we have these at various scales and angles or rotations to be able to detect kind of where we are in the body and the amount of contrast between a bone and soft tissue and these sorts of things. We can also take the contoured anatomy, like for example, the prostate, and we can calculate the distance along the X dimension, along the Y and the Z dimensions. We can also look at the distance to the femur, and that gives us overall not only a representation of what the image looks like, but a representation of the actual patient's geometry. Stacked together, this now gives us a feature space that represents the overall patient, and we can try to learn the relationship between that feature space and the dose distributions. So how do we do that? The first step is for every patient in the training database, we learn something called an atlas regression forest. So this is basically a way of encoding that particular patient's treatment as a function of their features. So we start off here at the top of the tree, where we don't actually know anything about that patient's treatment because we haven't really observed any features yet. So here we have kind of a uniform distribution of dose. As we progress down the tree, what we do is we learn additional examinations of those features or additional rules of those features. For example, that we have low density, that the gradient is medium scale, is very large at that point, for example. That gives us a bit of a narrow distribution. And as we then progress down this, in this case, this hypothetical tree, we might eventually figure out that we're inside the heart, and therefore we have a much more narrow distribution. Now, this tree is hypothetical, it's only a few layers deep. In reality, it learns very, very deep trees that are able to then characterize down to the individual voxel of a patient how much radiation should or shouldn't be present. Versus if we looked at the distribution, for example, once it figured it was inside the lung, it should have a very low probability of having dose. So now we have, for example, of a database with 3 patients, and these are just head and neck cancer patients here for visualization. Then we'll have 3 of those atlas regression forests, 1 for each patient. And then we need to learn which patients are similar to another. So we haven't really answered the question yet of what similarity means. So how are we gonna do that? Well, what we can do is we can take every patient and compare them to every other patient in the database by using the atlas regression forest from patient A to plan to make a radiation therapy plan for patient A. And obviously patient A is a good plan for itself, so that works. We can also use the atlas regression forest from patient A to plan patient B and see that that makes a good plan. And correspondingly, we can also see that, for example, for C, it doesn't. So we can see here that A actually has a very large area of tumor, whereas C has a much smaller restricted area. So C might benefit from increased organ sparing, for example. We can do the same thing for patient B, comparing it to all of the other patients, and the same thing for C. But what we notice is that because C has increased sparing, it may actually be a good plan for patient A if we're able to achieve that level. So this relationship is not necessarily symmetric. And we can go out and fill the rest of this cross-validation table out. So that's the first step. So what does it kind of look like for the machine learning? Well, the machine learning now has a goal. It wants to be able to predict that metric of how well a given atlas will work for a novel patient, but it needs features to be able to learn it on. So what we do is we look at the features that the ARF actually learned for each patient to see what features are relevant to predicting dose. Since, for example, if we were to just take this image here and compare it to a novel patient, the bulk of the image isn't receiving any dose. And so the bulk of the image doesn't actually matter. For example, if I took the same patient and imaged them over 5 days while their arm was moving around, their arm doesn't impact the treatment. And yet it would create a significant difference in terms of just straight differences between those two images. Whereas if we look at the features from the actual model, we'll get features that are relevant to dose. And so that's what we kind of see in this middle column here. Here, constant colors represent all of those voxels belonging to one singular leaf in the Atlas regression forest. So we can see is that a very high resolution of detail is needed around the target because the dose distribution has to be very shaped there. Whereas all of this dark red, none of this receives any radiation in this particular breast case. And so all of it can be kind of considered similar. On the far right, we see how the computer kind of views this. This is a density estimation, so it's a probability of observing particular features given the actual image. And then what we can do is we can compare this for a learned ARF to a novel patient on the bottom. And we see that for this novel patient, the image gets viewed by the Atlas regression forest in a very similar way. So like gets kind of cut up or over segmented in a similar way like we see here in the middle, and thus results in a very, very similar density estimate. But if we move to a different patient, and we can notice just toggling back and forth, the difference between these two patients is that the tumor is moving around the breast. And as the tumor moves around the breast, you might notice that there's a lot more lung involved in the treatment on the top than on the bottom. Because in this bottom treatment, more lung can be spared and thus less lung radiation, which is obviously a good thing. So this patient gets looked at very differently by the Atlas regression forest, and thus ends up at a very different density estimate. And the machine learning will then be able to tell that these two patients are very different from a treatment perspective. So let's look at how that works. So imagine now we've done that for all pairs of patients in the training database, and we've calculated for these synthetic examples, if we only have 4 leaves for every tree, we've then calculated the distance between all of the leaves on all the different trees across all the different patients in the cross-validation set. So we might learn, for example, that A is very similar to itself, but due to some random sampling, it might be a little bit different for one. That's okay. It's a little bit more different for B, and it has a heavy difference for C. And then what we can do is we can feed these sets of features into another machine learning model, which we also used a regression forest for, but we could have used SVM or deep learning or any other method, and try to predict the actual match between those patients' plans. So we use the features taken from using ARF-A on patient B to predict that ARF-A on patient B resulted in a good clinical plan, and to also predict that ARF-A on patient C resulted in a bad clinical plan. And thus we've learned a distance metric or a similarity metric between the patients. So how does this overall pipeline look? Well, for a training patient, we basically have the CT image. It's been delineated and also has all the dose. We can calculate the features. We can do the Atlas regression forest training. We can do the accuracy estimation, get the features for that via cross-validation, and train the Atlas selection models. Then for a novel patient, we can do that same feature extraction set. We can combine that with the learned atlases to actually figure out which the most similar atlases are for that patient by running them through the Atlas selection framework. We can then infer the dose using a probabilistic method from all of those most similar atlases. And then we do something called a conditional random field spatial dose optimization. And I won't go into the details here for time, but basically what we're doing there is trying to find the most likely spatial distribution of dose from those probability distributions that results in something that's actually physically deliverable. Because of course, the underlying machine learning would be very happy to put, say, a gap of dose in the middle of this patient, even though, as we mentioned before, radiation has to travel along a straight line, and so that's not physically allowable. We then go through dose mimicking to be able to actually figure out how to get that big robot from the beginning with the arms that rotates, how to get that whole thing to actually create this treatment plan. And the result is a finally clinically deliverable treatment plan that we can actually treat patients with at our hospital. So we designed a number of study phases to kind of go through over the years. And we'll see why each of these turns out to be important as we progress through. So we started off with technical metrics. So the models were trained and tested at Princess Margaret Cancer Center. We had over 500 retrospective validation cases. We went 9 different treatment sites, so breast cancer, lung cancer, etc. And we looked at the accuracy in terms of the percentage of voxels that had similar radiation to their clinical counterparts. And overall, we learned that it worked quite well and that it took about 40 to 60 patients on average to train a model, which is actually a reasonably small number of patients in comparison to some other approaches. We then went on to clinical metrics. So technical metrics, those are what you'll see, like basically looking at the AUC. It's what you see in a lot of journal papers. We went one step further. And so we actually created the clinically deliverable plans. We compared them to the machine learning plans. And I'll just kind of fade out some of the clinical metrics that the clinicians look at. What's important here is along the bottom. So where it's blue, the machine learning hit a unique criteria that the clinical plan did not meet. And when it's yellow, the clinical plan hit a unique criteria that the machine learning did not meet. So for example, in this case, the blue plan was able to achieve better sparing to the mandible. And so you'll notice there are some clear wins for machine learning, there's some clear wins for clinical, and there's a number of ones where there's a trade-off. And where these trade-offs occur is really where we need a physician to actually look at the overall patient and decide what's best for their particular care, given their age, disease characteristics, etc. So this is where really a clinical study is needed. So that was kind of the next phase. And so here for 17 retrospective prostate cases, we had 3 blinded clinicians review each plan, and we used a majority vote to determine the best treatment plan. And what we actually observed was that the automated plans were better for 12 out of 17 of those cases, equivalent for 3, and worse for 2. So overall, in the majority of cases, the AI was equivalent or better, and better in about 70%. So how does that work? Given that we trained the AI at Princess Margaret, how does it then beat data at Princess Margaret? And so part of the reason for that really comes down to we have a bit of a built-in outlier detection. So imagine that patient C was not well planned. So the clinical team was very stressed that day, didn't have much time, et cetera, and so it just didn't end up with the best quality of care. That patient will be a poor atlas for all of the other patients, and therefore will have a low score. And for a novel patient, we always try to predict the ones with the highest. We always try to use the atlases, that are predicted to have the highest scores. So there's a kind of a bias towards the best treatment plans within the system, which ends up being a good thing. So that was still retrospective, and these now clinicians are looking at it, but we still wanted to actually treat people. And so the next step was to design our clinical study. We wanted to design the study in a way that did not perturb or interfere with the clinical environment in any way, shape, or form so that we could actually have this for as many patients as possible. And so we did it in parallel. So every single prostate patient that came into the hospital ended up with a manual treatment plan and a machine learning-based treatment plan. And then the clinicians would do a blinded head-to-head comparison between the 2 plans, decide which plan they liked more, and that plan would go through peer review and quality assurance, just like every clinical plan does at the hospital. It'd be selected for treatment, and when selected, it would go forward and actually treat the patient. So here is the form that the physicians reviewed in the head-to-head comparisons. They're blinded as to whether A1 was automated or manual and vice versa. And they would look at particular metrics along those treatment plans and see which they preferred for A1, for example, or if they thought they were equivalent. They would look at whether each plan independently was acceptable or not, so whether it was safe for treatment or not. And then they could check off which plan they preferred, if they were equivalent but wanted to use one plan, or if they didn't like either plan and they needed something else to, of course, protect patient care, since obviously that's always the priority. And finally, we did actually a modified Turing test. And so effectively what happened is we actually asked them which plan they thought was the automated plan to gauge their ability to identify AI versus manual. So the results were fantastic. And it started off, we'll show that there was actually a median time savings of 71 hours per patient. And a lot of that actually comes down to the realities of fitting in a clinical workflow. So even if a human takes 2 to 3 hours to create the plan, that human may not be available until 4 in the afternoon, even though the contouring was done at 8 in the morning, or they might not be available until the next day. whereas the AI is available the second that CT scan and those contours are ready to go. So the AI fits into a workflow in a lot more efficient manner than having a lot of back and forth between different members of a clinical team. Now let's look at the accuracy. So we split it into two phases. There was a simulation phase. So that's where we did the blinded review, but it's retrospective. And then we did a deployment phase. And the deployment phase, prospective, all patients, when AI was selected during that phase, got treated with AI, et cetera. So what we noticed is that during the simulation phase, 92% of the radiation therapy plans created by the AI were acceptable. During the deployment phase, that was 86%, so a small drop, but not statistically significant, or 89% overall. So that's actually a pretty solid result. So that means about just under 90% of the time, the AI created a plan that was safe, which is a phenomenal win. We also looked at the ML algorithm being applicable. And so what happened was, for a number of the cases, the physician requested something outside standard of care. And so the clinical team creating the plan actually had to talk to the treating physician to figure out exactly what they wanted to occur, which unblinds the physician onto the treatment plan. And so they had to basically be excluded from part of the analysis. We then looked at from those applicable plans, how often machine learning was selected. It was selected in 83% of the time during the simulation, but only 61% of the time during deployment. And because that's a reasonably large gap, we decided to investigate this. So let's look at some of the possible causes. So we looked at, for example, whether the machine learning itself deviated across the year or so that this was live. So we took basically some quantitative measurements of quality, so how much radiation was going to each of the organs, to the target, et cetera. And we looked at the superiority of the machine learning plans to the clinical plans over that time. We found that 81% of the machine learning plans were quantitatively superior during the simulation phase versus 79% in the deployment. So again, statistically not significant. So we figured the machine learning is consistent across the two phases. We looked at the ability of the treating physician to identify the machine learning plan between the two phases, and they remain consistent as well at 77 versus 74% respectively. So that's their Turing test. And then we looked at whether the treating physician thought they were choosing the machine learning plan. And that drops from 68% to 49%. So what that actually represents is that during the simulation phase, they picked a plan they liked, and they were overall 94% likely to have 83% likely to have picked that plan. And they thought it was the ML plan 68% of that time. However, during the simulation phase, it was only 49% of the time when they picked machine learning that they thought it was machine learning. So they actually picked machine learning and thought it was a clinical plan. So they had some level of bias against disbelief about machine learning being clinically acceptable. We also looked at whether or not the machine learning plan was selected when it was superior upon that consensus quantitative review. And it was 92% in simulation and 71% during deployment. So overall, what we actually conclude from this is that when there's a degree of risk for the patient, the physicians become a lot more conservative. So there's a lot more conservative views or behavior in a clinical study versus in a simulated study. And this turns out to be important because this means that the clinical setting impacts the willingness for AI. And so this matters a lot because if we think about the journey that most kind of papers go through in AI, they have the technical phase, they might look at technical metrics, a smaller number of papers look at clinical metrics, an even smaller number of papers do retrospective clinical review with expert physicians actually looking over the results, and an even smaller number of papers actually then do clinical deployment. And what that means is there could be a very large performance gap from the clinical simulation to clinical deployment. So we might be overestimating how well AI will actually perform in the wild. But it's not all gloom and doom. So it's important to focus on the fact that it was still 61% in that deployment phase were better than our current standard of care. So the majority of the time, the AI came up with something that was better for the patients. And thus the physicians actually, despite this, are very happy with the AI. And so today, AI has become the standard of care at our hospital for prostate cancer. Every patient gets a machine learning plan. And only when the physician doesn't like the machine learning plan do they actually then ask for a manual plan to be created to address those inefficiencies. Okay, that's all I have. So thank you very much for having me.
Thank you, Dr. Chris, for the insightful talk. We have a question here. So the question is, I'm not sure I understand this. A is similar to C, but C is not similar to A. I think in one of your similarity diagrams.
Oh, yep. The reason that the relationship doesn't have to be symmetric is because, for example, a patient could have a organ in the field of view of the treatment for, let's say, for patient C, that the cancer is low enough down that the thyroid is in the field of view. So that might be the case for patient C, but not for patient A. So if patient A, as a result, the model has no idea what to do with the thyroid, it will not create a good plan for patient C. But patient C knows to avoid the thyroid. Patient A doesn't have a thyroid, so extra avoiding an organ that isn't there doesn't hurt it.
Thank you. Does the progression of cancer matter for this model?
So that's a great question. So it absolutely does, and it is taken into account. So that's in selecting the actual treatment protocol. So what we do is we train a set of these models for every treatment protocol. So there's multiple treatment protocols for prostate, multiple treatment protocols for breast cancer, et cetera. And then depending on the individual stage, et cetera, of the patient, the physician actually prescribes an amount of radiation. And so that's irrespective of AI, that's currently what's done at the hospital. And then once they're prescribed that certain amount of radiation or radiation in combination with chemo and combination with surgery, et cetera, then that particular treatment model is used.
Great, thanks. Is retraining done in the pipeline based on the feedback from ML model?
Sorry, thirsty. So that is a very good question, actually. So under this, the model is actually Health Canada, FDA, and Euromark approved. And currently under FDA guidelines, which Health Canada follows, retraining is not allowed. It's illegal. So the FDA actually approves a particular model. So they have approved this, and I think we trained on 98 patients. So if we add 99, it's a new model, and we have to go back through FDA approval.
Oh, okay.
So that's misguided and should hopefully change, but currently we cannot. Otherwise, I agree, what we really should do is, given the fact that for 61% of these cases we created a better plan, we should scrap all of the old data, retrain from the data from our study, create a better model, and then use that going forward. Absolutely, it's just we have to go back through FDA.
Yes, yes, true. That's good to know. Okay, we have a couple more questions. Would you train your model different for treatment areas with more risk of changes in anatomy, like abdominal treatments where bowels can move?
That's a great question. So that's already built into the care. So when they do that prescription, part of that prescription includes something called a margin. Yeah, so on the prostate, for example, they use a 5 mm margin. So they actually, you'll notice that the delineations are a little bit larger. They then go kind of one delineation larger than that. They go about a 5 mm ring around that, and they say they have to treat everything within that ring to account for patient setup errors or movements. So that's kind of built into the model. And then we're also looking at, for the future work, being able to re-image the patient using MR technology and other types of imaging technology daily as they come in for their treatments, and then adapting those treatments to their daily changes in anatomy as well. Before, that wasn't really feasible because, again, like, so the patient would come in that morning, be imaged, and now it would take, we saw, a couple hours to generate the contours, couple hours to generate the plan, et cetera. Just, it wouldn't fit in time. But with machine learning making everything more efficient, it starts to become practical.
Sure. Another question is, do you think RCTs are needed for applications like this?
So that's a great question. So we did not do a randomized control trial in this particular case. We could have. This was actually done under a quality improvement initiative. So we got a waiver for a randomized control trial. And a trial would be useful to go through kind of a multi-center thing and see if, instead of physicians preferring the AI plan, if the AI actually led to improved clinical outcomes. So it's a great follow-up step to do, just takes time.
Sure. Okay. I think one last question. What is the commercial name of the application? What kind of regulatory pathway was followed through the FDA?
That's a good question. So assuming I understand your question correctly, the product is commercialized through research laboratories as part of their RayStation treatment planning software. I believe they call it machine learning planning or auto planning. I can't remember their marketing name. Obviously, I'm not in charge of marketing. I work for the hospital. The regulatory pathway, so how it basically worked is we created the technology, we patented it, we licensed it to the company, we built a version of the technology with the company. The company then applied, actually, sorry, one more step. We then trained the models with the company on the data set. We verified that those models worked in the same way that the machine learning models that I had built at the hospital worked. We then submitted that data with the company to the FDA, and it went forward for approval that way.
Okay, great. Yes, on behalf of TMLS team and everyone here, I'd like to thank you, Dr. Chris, once again for the talk. And I encourage attendees to visit our partner booths to enter in some exciting giveaways. Thanks again, everyone. Have a great day.